How do we understand complex pulsar timing in neutron stars? Imagine a lighthouse beam sweeping across the night sky with perfect consistency. Now picture that lighthouse being a neutron star spinning hundreds of times each second. That's what pulsars do, and scientists have found clever ways to understand their timing. Pulsar timing involves measuring the exact moment each pulse reaches Earth. These pulses are incredibly regular, acting like cosmic clocks that help us study the universe. But sometimes, the timing isn't perfect. Tiny variations happen, and these small changes tell us a lot. They can reveal how the neutron star is slowing down, how it's moving, or if it has companions orbiting around it. Neutron stars are born from massive stars that explode in supernovae. When the core collapses, it becomes a neutron star, incredibly dense and tiny, about the size of a city but with more mass than our sun. These stars spin very fast and have strong magnetic fields. Their magnetic poles emit beams of electromagnetic radiation, which sweep through space like lighthouse beams. Because the magnetic axis isn't lined up with the rotation axis, these beams appear as pulses to us on Earth. To understand the complex timing, scientists look at the deviations from perfect regularity. The first factor is called spin down. Over time, pulsars lose energy through electromagnetic radiation, making their rotation slow very gradually. By tracking this slow change, scientists can estimate how old the pulsar is and how strong its magnetic field might be. Next, internal changes inside the neutron star can affect timing. As the star cools, parts of it can turn into superfluid states, which can change how it spins. If the pulsar is in a binary system or has planets orbiting it, its motion around the system's center of mass causes predictable timing variations. These variations help scientists measure the mass of the companion and the details of the orbit with high precision. Pulsar signals also pass through space filled with plasma, which can cause delays and distortions. Scientists must account for these effects to keep their measurements accurate. To make sense of all this, researchers develop detailed models that fit the observed pulse arrival times. These models include the pulsar's rotation rate, how it's changing, its orbital motion, and the effects of space plasma. Using these models, scientists can predict the pulsar's behavior over many years. This helps test Einstein's theory of general relativity and even detect gravitational waves. Understanding how we interpret pulsar timing also shows how important long-term scientific work is. It requires continuous observations from radio telescopes around the world and advanced data analysis. Supporting these efforts helps us learn more about the universe, improve technology, and stay at the forefront of space science. The techniques developed for pulsar timing could also help in navigation and timekeeping in future space missions.